Okay, so first I want to dedicate this video to my future baby daddy, Jeremy Lynn, call me. Now, on to the serious business. I wanted to use example or problem number 414, solve it, but use it as a catalyst or a problem for teaching you the node voltage method of circuit analysis. So the node voltage method is a powerful technique for finding the voltages and the currents of a given simple circuit, a planar circuit. So what it is it leverages Kirchhoff's current laws in order to solve for all. Basically, when you're doing circuit analysis, what are you doing? You're really trying to find useful information like what's the current going through here, what's the voltage drop here. That's what technicians are always doing. If there's a problem, what do you need to know? You need to know the voltage. You need to take voltage drops and then find out if you have an open or a short and see where the problem is. So that's what, or measure a current. Maybe something, you have an open somewhere that is causing too much current to go through somewhere, and that's causing your equipment not to work right. So when you're doing circuit analysis, that's what you're doing. You're finding voltages and currents. And when you're modeling, you want to know what you should get versus what you're getting in the real world. So the node voltage method is a powerful technique for finding voltages and currents everywhere in a simple circuit. So the way that it works is the node voltage method uses Kirchhoff's current law. It says that current into a node must equal the same as current out of a node. And so let's take a step back. What does that mean? What does a node mean? A node is just a regular node is a point that connects two or more circuit elements. So in that case, this is a node right here. This is a node. This is a node. It connects these three. This is a node. This is a node. So they connect like this node here connects a 5 amp current source, a 20 ohm resistor, a 40 ohm resistor, a 7.5 amp current source, and this is a node that connects a 40 voltage source and a 12 ohm resistor. Kirchhoff's current, the node voltage method only uses the what's called an essential node. An essential node is a node that connects 3 or more circuit elements. So this is not a node that we would use. We would not use this as a node for node voltage analysis. We would use a node like this right here. This connects 4 circuit elements. So we can use that in order to solve for the voltages and the branch currents. So that being said, let's identify the essential nodes in this problem. Remember, essential nodes are nodes that connect 3 or more circuit elements. So it's going to be this one right here, which connects the 5 amp, the 20 ohm, the 25 ohm, and the 12 ohm resistor. That's one node. This is a second node, right? A 5 amp, a 7 amp, a 40 ohm, and a 20 ohm. This is a third node. It connects a 7.5 amp, a 40 ohm, and a 40 ohm. This is a fourth node. It connects a 25 ohm, a 40 ohm, and a 40 volt. So that is step number 1, is to identify all of your essential nodes. Step number 2 in the node voltage method is to pick one of those nodes as your reference node. It doesn't matter which one you pick. You can pick this one, you can pick that one, you can pick that one, you can pick that one. You will always end up with the same mathematics. The math will always work out the same, and you'll end up with the same branch currents because the power will be, or the voltage drops will be distributed the same across, regardless. Well, actually, that's not true. You would get something different, because if I pick this to be the node, then you would get the different math. But if you're in this problem, we're calculating power dissipated. So the power dissipated will all sum up to 0. So you pick a node is the second step. So what we're going to do is we're going to name these nodes. We can call these V1. We're going to call this V2. And we're going to call this V3. And we're going to take this as our reference node. So now to recap, Step 1 is identify your essential nodes. Step 2, pick one of them to be your reference node. Most people just pick anything nearest to the literal ground to be in a lot of circuits, in most circuits that you see, you have a ground, typically that's a ground, and the ground is because the ground does connect everything above it, right? It's an essential node, and it's a very natural point of reference to take. So anyways, I picked that to be my ground. That's step number 2. Step number 3, I need to explain what's happening at each of the nodes for our calculations. We're going to start calculating branch currents. Don't forget, the node voltage methods uses Kirchhoff's current law. So Kirchhoff's current law says that the sum of all the currents coming in and out of that node is equal to 0. So what's going in must be accounted for going out in one of these branches, right? If something's coming in here, it's got to come out there somewhere, right? So I can account for it if it's +1 and it's -1, so it sums to 0. And that's the premise of that. The other thing to understand about the node voltage method is, since we don't know what that current is, we're going to use Ohm's law to calculate current. Remember, Ohm's law is I is equal to V over R, right? And in this case, if I don't know what this is, then I can take the difference in the voltage between the resistor, right, delta V, and I can calculate over R, and that will give me that branch current. Now, that's the second thing you need to know about calculating a branch current at a node. The third thing you need to know about calculating a branch current at a node is, the way for this to work is we calculate it as the current is moving away from, that's going to be defined to be the positive direction of the current. And that, which means that whatever node you're calculating your current at, you start at that node for your calculation. So, for instance, in this one right here, if I want this current, the I sub 12 ohms, I'm going to start with V1, the tail, and then I'm going to go subtract the second voltage, which in this case is minus, right? Minus a negative 40 volts. If the node hits a voltage source, you take the sign that's closest to it. So in this case, you subtract, because we're finding the delta, the difference, right? And then you divide that by R, and that's how you calculate the branch currents at the node. So that's the second thing you need to know. And of course, you do that for all of the branch currents at a node. Okay? So the biggest mistake that people make when they're using the node voltage method is when they come. It's when they get into a rhythm of, they start taking this voltage divided by whatever is the circuit element. And then they forget to look at the circuit element, and it might be a dependent voltage source. So they'll take voltage 1, voltage 2 divided by a dependent voltage source, which is not even a number that makes sense. So remember, bear in mind that even though we're finding voltages, we are using Kirchhoff's current law in order to always bear it in mind. What am I calculating? It better be a branch current. So let's go ahead and find the 3 equations. We have 3 unknowns, V1, V2, V3, therefore we need 3 equations, and those 3 equations will come from the the node voltage method, which again, I'm emphasizing this because it's important, because this mistake happens a lot. We're using Kirchhoff's current law at voltage 1, V1, at V2, and at V3. So now, in this problem, we're asked to find the power dissipated by each of the circuit elements, and to verify that power developed is equal to power dissipated. And of course, power is voltage times current. So we can't possibly solve this problem without finding the currents, and almost all problems that you have, you can't do anything without knowing the voltages and the currents. So let's get started. Applying the node voltage method at the V1 node. Okay, so again, KCL, all the currents are must sum to 0. So this branch current is going to be V1. We always start at the node because we're calculating the currents away from it. Minus, you start from the tail. If the nose hits a current source, you take the sign that you hit first. That's going to be negative 40. over 12. Notice that this is a current, right? Delta V over I is equal to V over R, or this current is going to be delta V over R. And that's what we've got. Voltage over a current over resistance is equal to current. Plus, okay, this is where people will make mistakes. People will go V1 minus V2 over 5. And no, that's not correct, because we're doing KCL, which means summing the current. This is already a current source, so it's just plus 5. Here we have, and of course it's plus 5 because it's already going away, and that's defined in the node voltage method to be a positive current. The third is V1 minus V2 over 20. So V1 minus V2 over 20. And the fourth branch current is going to be V1 minus V3, V1 minus V3 over 25. All of those currents have to equal 0. Current into a node must equal current out of the node. So now we're going to rewrite this equation in a way that is going to make it easy to enter into our engineering calculator. So find all the coefficients of V1 over here. We have 1, 12. Here we have plus 1 over 20. Here we have 1 over 25 plus, okay, now group all the V2 coefficients together. We have negative 1 over 20, and then all the V3 coefficients together, plus V3. We have negative 1 over 25, and that's all of it. And then all of that has to equal, any constant has to be moved to the other side. And this is going to be a plus and a negative, and a negative is a positive. But I'm going to move it over to the other side, which makes it a negative again. So I'm going to have negative 40 over 12. And the other constant I have is a plus 5, which is going to become negative 5 when I move it to the other side of the equation. That's my first equation for one of the three that I need. Now the second equation is going to come from my second node, which is V2. So now we have, so we want to calculate this current, this current, this current, and this current, right? So let's start at the top. This is already 5 amps coming in, so since we're defining positive current to be away from the node, that 5 amps is going to be represented as a negative 5. So this current here is going to be calculated by V2 minus V1 plus V2 minus V1 over 20. Here we have another current going into the node, so that's going to be negative, minus 7.5 amps. And then the fourth branch current is going to be V2 over 40. That's going to equal 0. Okay, so now I'm going to rewrite this for my calculator. Gather all of, oops, this should be V2 minus V1. Gather all my V1 coefficients together. This is negative 1 over 20 plus V2. All of my V2 coefficients, this is 1 over 20 plus 1 over 40. And then V3, there are no V3, so I'm going to put a 0 there. Constants go over the other side. I have negative 5 and negative 7.5, so they become positive on the other side. And that's my second equation. Now to find the third equation that I need at V3. So, you know what? I think I prefer to have, pardon me, I prefer to have V2 right here. I'm going to redo V2, or V3 right here. Excuse me. Yes, I prefer my, my reference node to be right here. Hold on one second. Do I really prefer that? Yes, I do. I do prefer that. So I'm going to redo this one. And the reason why I prefer to do that is that this is a node that I picked when I worked this out initially, and I've already calculated the voltages. Remember, if you have like 10 volts, 20 volts, and 30 volts, and you pick this as your point of reference, right? Then the V1 is going to be 10, and then the V2 is going to be 10, right? But if I pick this as my my point of reference right here, then V1 is going to be 30 volts with respect to that, and V2 will be, so I just want my answers to match what I have already worked out, and the way I had it initially, because I've already calculated the numbers with respect to the original one, so I'm going to stick with what I did originally, and I did that. So I chose this as my V3. So I'm going to redo my second equation. My first equation is the same because my first equation doesn't touch V3 at all. But like I said, maybe I'll do a video. Maybe if I have time, I'll do the video and I'll calculate the voltages. With this is V3. It'll be different because it's a different point of, some of the numbers will be different, but when we calculate the power dissipated will still equal power generated. So power will all still sum up to 0. So at V3 right here, we're gonna, so at V2, with this as V3, we're gonna have, this is gonna be -5, right? We have the current going into this node. We still have plus V2 minus V1 over 20 plus -7.5 plus V2 minus V3 over 40. That's going to be equal to 0. And then we're going to rewrite that for our calculator. For V1, I have a -1 over 20. And then for V2, I have a 1 over 20 plus 1 over 40. And then for V3, I have a -1 over 40. And all constants get moved to the other side. I have a -5 here and a -7.5 here. They become positive on the other side. Okay, so the final one that I have to do is at V3. So no voltage at V3 is going to be V3 with respect to the reference node over 40. I don't have anything to, any of the voltage to subtract. And then this branch current is going to be V3 minus V2 over 40. And then this current is, this is already a current and it's already positive, so we're going to go plus 7.5. All of those equals to 0. Okay, so now we're going to rewrite this in a way that's easy for our calculator. There's no V1, so 0 V1 plus V2. We have a -140 for coefficient for V2, 140. And then for V3 plus V3, we have 140 plus 140. Okay, and positive 7.5 becomes -7.5 over there. And let me just verify, because it's so easy to make mistakes on simultaneous equations. 112, 120, 125, maybe 120. Where is my first equation? B3. Oh, okay, I'm glad I did that because I made a mistake in my first equation. So let me do the first equation again. Okay, so first equation is V1 minus -40 over 12 plus 5 plus V1 minus V2 over 20 plus V1 over 25. Okay, so now V1, 1 over 12 right here, plus 1 over 20 right there, plus 1 over 25. Oh dear. That has to equal 0. Okay, V2, our coefficients are negative 1 over 20, and that's it. And then for coefficients, I'm going to move that negative 5 over. And then I have a negative and a negative is a positive, but when I move it over, it becomes a negative again. Negative 40 over 12. Okay, so now let me double check since, again, it's easy to, I want to put a placeholder for my calculator. Plus V3, I have 0 V3s, so that's going to be negative 40 over 12 plus minus 5. Okay. Alright, so my second equation, 120, 140, negative 140. Okay, that's good. My third equation is negative 40, 1 over 40, 1 over 40, negative 7.5. Okay, so when you enter these values in your simultaneous equation solver, you should come up with V1 is equal to negative 10, V2 is equal to 132, V3 is equal to negative 84 volts. Okay, so again, I just want to emphasize that the only reason why I swapped it was because I had solved this problem already. So I had the voltages solved. It wouldn't make any difference if I had, if I have the time, I'll just go back and prove to you that you could have easily picked this as V3 and that as the ground, and you will come up with different voltages, because remember what a reference node is the other end. The first point is your voltage, the second point is your the second probe of your voltmeter. So of course if you change the point of reference, that number will change. So I had it here right now, but before when I initially wrote it, I had it right here. So of course the V1 will be different if I take my 2 voltmeter and I do that. So in a way, to think that there's a right answer for voltages is, it's arbitrary. Sometimes, but what they end up doing though is they make the choice of the third voltage to be pretty easy. So anyways, with this one, the question is about power. So let's go ahead and solve for the power. I have 1, 2, 3, 4, 5, 6, 7, 8 circuit elements. So let's just go in an orderly fashion. The power from the 40 volt source, okay? The current is going to be V1. I'm going to calculate this current, right? So this current, if I take just positive, calculate in such a way that it's positive current, I'll have V1, which is negative 10, minus V2, which is going to be negative minus negative 40 volts over 12. That's going to be my current calculation if I just use this convention right here. Times, what is my voltage? The sign of the voltage is determined by what the nose of the current hits. In this case, I've calculated the current to go like this, and the nose of the current is going to hit the negative sign. If the nose of the current, if I had done it like this, right, then that's the tail end. The tail end is leaving the negative, so the nose end would be entering the positive. So that would make my voltage a positive voltage. But then I would calculate my current starting with this, a negative 40 minus that. So the convention, knowing what's happening with your current, will tell you whether this voltage source is developing or absorbing power. So in this case, the nose is entering the negative end, which makes my voltage a negative 40 volts. So therefore, power developed is negative 10 plus 40 divided by 12. So that's my current. I have, times negative 40. And let me verify. I have negative 100 watts, which means that particular voltage source is developing power. Resistors always dissipate power. So let's do P sub 12 ohm. Doesn't matter what it is, P is V squared over R, so V is going to be delta V, V1 minus 40, minus negative 40, squared over R, which is 12. This is going to give me, let me see, where is my calculation? V1, V2, V1 minus 40. Where's P sub 12 ohms? Okay, so then I have negative 10 plus 40 over 12. That's going to get squared. And I have negative 10 plus 40, square it, divided by 12. It's going to give me 75 watts. I'm going to start putting the numbers over here. So this is going to be negative 100 watts. This is 75 watts. Okay. So now let's do the calculation for the 5 amps. So P sub 5 amp is going to be VI, right? And we know what I is. I is 5 amps. So what is V? V is V1 minus V2, which is going to give me 5 times V1 minus V2, negative 10 minus 132, and that will give me negative 10 minus 132 times 5 will give me negative 710. Negative 710 watts for that one. So the next one we need to find is the 20 ohms. So P sub 20 is equal to V squared over R. V is going to be, it doesn't matter, it's getting squared, so V1 minus V2 squared over 20. So that's going to give me negative 10 minus 132 squared over 20. So 10, 132 squared divided by 20. So this is going to be 1008.2 watts. Next one, let's do this one right here. So this one is going to be V sub 25 is going to be V1 squared over 25, and V1 is going to be negative 10 squared over 25. That gives me negative, so 10 squared divided by 25. This gives me 4 watts. Let's do this guy here. This one, V40, is going to be V squared over R, which is going to be V3 squared over 40, which is negative 84 squared over 40. So 84 squared over 40. V40. Okay, so then this gives me 176.4 watts. What's left? This one's left. So this one is going to be P40. Power dissipated by that 40 ohm resistor will be V squared over R. And V is going to be V2 minus V3 squared over 40. Okay, so V2, this is going to be 132 minus negative 84 squared over 40. So 132 plus 84. This gives me, let me double check. Okay, so this gives me 1166.4 watts. And then the 7.5 amps is P sub 7.5 amps is equal to VI. So V then is going to be V2, tail to head, is going to be V3 minus V2 times 7.5. This will give me negative 84 minus 132 times 7.5. Negative 84 minus 132 times 7.5 gives me negative 1620. Okay, so now we need to prove that power dissipated equals power developed, and that power and energy are conserved in a closed circuit. The negative numbers are the circuit elements that are developing power. The positive numbers are the circuit elements that are dissipating power. So the sum of the development ones are, we have negative 100 minus 710 minus 1620 gives me 100 plus 710 plus 1620. The circuit is developing or generating 2430 develop. Now the positive numbers, we have 75 plus 4 plus 176.4 plus 1008.2 plus 1166.4. That's 1, 2, 3, 4, 5. 1, 2, 3, 4. What? 1, 2, 3, 4, 5. Okay, so 75 plus 4 plus 176.4 plus 1008.2 plus 1166.4, and that gives me 2430 dissipated. So we have power developed equals power dissipated, and we prove that the circuit is balanced, and that is no matter what your point of reference is, your power developed and your power dissipated will work out to be equal to each other, and they should work out to be 2430. Okay, that's it for today.